In the year 1258, something strange happened, and then history went quiet. Across Europe, Asia, and the Middle East, chroniclers described a sun that refused to shine, famines with no clear cause, and plagues that arrived without warning. Empires weakened, cities vanished. But today, most people have never heard of it. There are no monuments, no official records, and the event that may have changed the course of the medieval world remains absent from nearly every modern textbook. What could erase a disaster of this scale, and who might benefit from its disappearance? Let's uncover a forgotten catastrophe, buried in ice, scattered in the margins of old chronicles, and silently removed from the story of civilization. The year the sky turned black. In the year 1258, written records across multiple continents documented an environmental anomaly with no known precedent. Chroniclers in England, France, Germany, the Middle East, and Asia describe skies that remained dark for extended periods, unusually cold summers, and widespread agricultural failure. These descriptions were observational rather than symbolic. In England, Matthew Paris of St. Albans Abbey wrote that sunlight grew dim, that the sun gave little heat, and that crops failed before maturity. According to his account, a severe famine followed, and bodies were buried in mass graves around London. In France, Cistercian abbeys near Dijon recorded poor wheat harvests and noted that the skies were filled with haze throughout the year. Administrative documents from Paris mention rising bread prices and public unrest. German chronicles from Hildesheim and Mainz referred to summer frost and a veil covering the sky. In parts of the Holy Roman Empire, food shortages were accompanied by rising grain prices and rural abandonment. These records reflected consistent atmospheric disruption across northern and central Europe. In Egypt, records from Cairo written during the Mamluk period describe a significant food crisis. Several surviving documents mention disruptions to the Nile flood cycle and abnormal weather patterns. Market instability and mass starvation were reported in multiple districts. Syrian chronicles, such as those compiled later by al-Makrizi, referred to unseasonal cold and crop failures across the Levant. These conditions coincided with accounts from Iraq, which recorded similar environmental stress before the Mongol siege of Baghdad. The Jingxi Dadian, a bureaucratic record from the Song dynasty in China, mentions extended periods of fog-like haze and major disruptions in rice production in Jiangnan. Officials in Suzhou and Hangzhou imposed emergency rationing policies. In Japan, the Azuma Kagami, an official chronicle of the Kamakura shogunate, noted that for most of 1258 the sunlight was weak, and harvests failed across multiple provinces. The phenomenon was not isolated. Records from Armenia, Vietnam, and parts of India make reference to poor harvests and weather irregularities occurring in the same year. Scientific evidence aligns with these reports. Ice core samples from the GISP-2 project in Greenland and the Dronning Maud land core in Antarctica show a sharp spike in sulfuric acid deposition beginning in late 1257 and continuing into 1258. This sulfate layer, measured in parts per billion, matches the magnitude of known stratospheric eruptions. The chemical signature indicates a high-altitude release of sulfur dioxide consistent with a volcanic event of exceptional size. Tree ring data supports the same conclusion. Dendrochronology samples taken from oaks in northern Europe and pines in Siberia show narrow growth rings beginning in 1258. The suppressed growth persisted for 2 or more years, indicating prolonged climate disruption. In the western United States, bristlecone pines show an identical pattern. The global scale of the biological signal confirms that the event affected atmospheric conditions across both hemispheres. Climate reconstructions estimate that global temperatures may have dropped by 1 to 2 degrees Celsius. For agrarian societies dependent on predictable growing seasons, this would have caused immediate crop failure and livestock loss. European feudal economies, already under pressure from demographic changes, were particularly vulnerable. Grain shortages led to rapid price inflation. In London, the price of wheat doubled between 1257 and 1259. Municipal records from Winchester and York reference emergency grain distribution efforts. In Hungary, land registries from 1258 show large tracts of farmland left uncultivated. In Bohemia, royal correspondences between King Ottokar II and regional governors mention food scarcity and tax exemptions for peasant households. In France, Bishop Guy of Auxerre wrote to Pope Alexander IV requesting relief for rural parishes suffering from famine. Across England, parish registers reported increased burial activity and shortages of laborers. Mortality rates increased sharply, although precise numbers are difficult to verify. In Egypt, Nile flood records show reduced water levels in 1258 and 1259. The flood, central to Egyptian agriculture, failed to reach expected benchmarks. This failure led to a collapse in the grain market and food riots in Cairo. Jewish merchant letters from the Cairo Geniza archive mention starvation, closed shops, and the movement of people in search of food. Persian sources from the Khwarezm region also note abnormal weather and a growing refugee population before the Mongol expansion reached the area. Despite these wide-ranging effects, no eruption was recorded in historical documents. Unlike Tambora in 1815 or Krakatoa in 1883, the 1258 event produced no known eyewitness account of a volcano erupting. No mountain name was preserved in writing. Modern researchers refer to it as a mystery eruption, or the 1257 event, based on the geological evidence. The absence of direct observation delayed recognition for centuries. It was not until the late 20th century that glaciologists and climatologists began to connect the disparate sources of data into a single hypothesis. In 2013, Frank Levine and his research team identified Mount Samalas, part of the Rinjani volcanic complex on Lombok Island in Indonesia, as the probable source. Geological surveys revealed deep pyroclastic deposits and caldera structures consistent with a VEI-7 eruption. Radiocarbon dating of buried forests placed the eruption in the late 1250s. Tephra analysis matched volcanic glass found in polar ice. The Samalas eruption, as reconstructed by volcanologists, released over 100 cubic kilometers of material into the atmosphere. This placed it among the most powerful eruptions of the last 2,000 years. Its aerosol cloud entered the stratosphere and circled the Earth, reflecting sunlight and cooling the planet. The event became visible only through its consequences: widespread hunger, atmospheric haze, economic instability, and demographic stress. It reshaped regional systems across continents, but remained unnamed, unrecognized, and excluded from most historical narratives for more than 700 years. The volcano without a name. For more than 7 centuries, the eruption that caused the global atmospheric collapse in 1258 remained unidentified. Despite ice core samples from Greenland and Antarctica showing a massive spike in sulfate deposition that year, no contemporary written source mentioned a volcano by name. The absence of a geographic origin created a scientific puzzle. In contrast to the 1815 Tambora eruption, which was extensively documented by Dutch colonials and travelers in Indonesia, the 1258 event left no known eyewitness testimony, no detailed narrative, and no preserved local account of ashfall or pyroclastic activity in any written archive of the time. The scale of the environmental impact was indisputable. Sulfate layers from the ice cores matched or exceeded those left by Tambora. The sulfate concentration peaked in late 1258 and persisted into 1259. Tree ring data from northern and central Europe confirmed significantly suppressed growth starting that year, with many species failing to show normal recovery until the early 1260s. Atmospheric modeling suggested a global temperature decline of 1 to 2 degrees Celsius, enough to shorten growing seasons, disrupt rainfall, and reduce crop yields across multiple climatic zones. This evidence implied that a major volcanic eruption had occurred, comparable in magnitude to other known cataclysmic events. But the eruption had seemingly gone unrecorded. Scholars initially hypothesized that the volcano might have been located in a remote or uninhabited region, such as Antarctica or the southern Pacific. Others speculated that it occurred in a region where writing systems were not in use, or where documents had not survived due to conquest, colonization, or environmental degradation. For decades, the eruption was labeled in scientific literature as unknown or unlocated. One candidate frequently discussed in early hypotheses was the El Chichon volcano in Mexico. However, tephrochronological comparisons and radiocarbon dating of surrounding deposits did not align with the 13th century timeframe. Another suggestion was a cluster of volcanoes in the Andes or the Alaskan Peninsula. But the chemical signature of those eruptions did not match the composition of ash particles retrieved from ice cores. The mystery persisted until a breakthrough in 2012, when geographers and volcanologists began investigating a large caldera on Lombok Island in Indonesia. The island, part of the Sunda Arc in the Lesser Sunda Islands, contains the Rinjani volcanic complex. South of its modern peak lies a massive caldera lake, Sagara Anak, formed by an earlier eruption. Field investigations led by Frank Levine from the Université Paris-Panthéon-Sorbonne uncovered a massive volume of ignimbrite and tephra deposits consistent with the VEI-7 eruption. The researchers conducted stratigraphic studies, examined buried soils, and performed radiocarbon dating on carbonized tree trunks sealed beneath volcanic layers. The results indicated an eruption date centered on 1257. In 2013, the team published their findings in the Proceedings of the National Academy of Sciences, identifying the Samalas volcano, now part of the Rinjani complex, as the likely source of the 1257 eruption. Based on geological data, they estimated the eruption released 40 to 60 megatons of sulfur into the stratosphere. Ashfall reached the island of Java and probably spread further across maritime Southeast Asia. Volcanic columns are believed to have exceeded 40 kilometers in height, allowing the material to enter the upper atmosphere and affect climate globally for more than a year. The eruption had no known written documentation in Indonesia from the 13th century. However, 19th century Dutch ethnographers recorded Sasak oral traditions from Lombok, which spoke of a city buried by a mountain explosion and a kingdom destroyed in a single day. These accounts referenced a ruler named Raja Salama in a city called Pamitan. Archaeological teams have since attempted to locate the ruins of this capital, though no definitive excavation site has yet yielded conclusive evidence of pre-eruption urban remains. The Samalas eruption's lack of a contemporary textual footprint can be attributed to multiple factors. First, the devastation likely destroyed any local scribal centers or archives. Second, the region's surviving oral histories were never transcribed during the medieval period. Third, neighboring polities in Java and Sumatra did not record the eruption in surviving court chronicles. It was not until Western glaciological and volcanological research advanced in the 20th and 21st centuries that the eruption's existence and probable location were confirmed. Tephra from the Samalas eruption has since been found in ice cores from both polar regions, confirming the eruption's global reach. Geochemical analysis shows a near-identical match in major element composition between tephra from Lombok and volcanic shards in the Greenland GSP2 ice core. These findings, combined with the precisely dated tree ring and climatic disruptions recorded across the globe, confirm the Samalas eruption as the most likely origin of the 1258 global climate anomaly. The magnitude of the eruption reshapes understanding of the medieval period. A single geological event, unrecorded in its own time, was responsible for sudden temperature drops, widespread famine, and indirect political consequences across Eurasia. The silence surrounding its name may have been due not to intentional omission, but to geographic distance, information loss, and the limits of historical transmission. Its identification was only made possible through the integration of modern earth sciences, climate modeling, and long-term historical research. Today, the Samalas caldera holds a crater lake, with the region showing signs of regrowth, but no written records from the time survive. This reflects a key weakness in pre-modern history. Catastrophic events could vanish from memory if they occurred where writing was rare or archives were lost. Samalas was identified not by legend, but by traces in polar ice, tree rings, and failed harvests far away. The volcano that darkened skies in 1257 remained unknown for over 750 years. A silent collapse in Baghdad. In early February 1258, the Mongol army under Hulagu Khan captured Baghdad, ending the Abbasid Caliphate's 500-year rule. The siege began on January 29th and concluded with the city's fall by February 10th. The Caliph, al-Mustasim, was executed shortly afterward. Contemporary sources describe the destruction in catastrophic terms, with reports of mass killings, burning libraries, and ruined infrastructure. But less often acknowledged is how environmental instability may have played a role in weakening the city prior to the siege. Baghdad in the 13th century was one of the largest cities in the Islamic world. Though past its peak as an intellectual center, it remained important for trade, religious authority, and regional governance. Its survival depended on complex irrigation systems connected to the Tigris River, particularly the Nahrawan Canal. Agriculture surrounding the city supplied food for a population estimated between 200,000 and 300,000. Disruption to this system could quickly create food shortages and civil instability. Several historical records mention signs of stress even before the Mongols arrived. The Egyptian chronicler al-Makrizi noted unusual prices and scarcity of grain in the region during this period. Persian historian Atta Malik Juvaini, who traveled with Hulagu, observed that Baghdad's population appeared weak and poorly provisioned. While Juvaini emphasized the military campaign, his description of deteriorating conditions prior to the attack suggests deeper systemic problems already in motion. Environmental data supports the likelihood of such disruption. Ice cores from Greenland show a major sulfate spike in 1258, corresponding with a large volcanic eruption, later identified as originating from Somalis in Indonesia. Volcanic aerosols from this event would have spread globally, reducing temperatures, shortening growing seasons, and disrupting rainfall. Tree ring studies from Anatolia and Lebanon confirm a drop in growth in 1258, which would indicate colder and drier conditions in the eastern Mediterranean and parts of Mesopotamia. Agricultural output in the region likely declined. While no direct yield records survive from Baghdad's fields, reports from Syria and Egypt mention delays in grain shipments and poor harvests. Letters from the Cairo Geniza, an archive of merchant correspondence, include concerns about rising prices and trade route disruptions in 1258. These references are brief but consistent with climate-induced food stress. Fewer shipments, higher prices, and localized shortages create conditions where urban centers like Baghdad become vulnerable. The Mongol campaign itself required massive logistical planning. Hulagu's forces included engineers from China, siege specialists from Central Asia, and tens of thousands of troops. Though the Mongols often avoided campaigns in winter, they moved against Baghdad in January 1258. The choice may have been strategic, taking advantage of a weakened, undersupplied city that's already facing environmental stress. The Tigris River reportedly flooded early that year, possibly from irregular winter rains or failed canal regulation. This made movement difficult, but may have further hampered the city's defense. During the siege, Baghdad's outer walls were quickly breached. There is no evidence of prolonged resistance. On February 10th, the city surrendered. What followed was extensive destruction. Giovanni estimated hundreds of thousands of deaths. Though modern historians question these figures, the loss was undeniably severe. The Nahrawan Canal system was damaged beyond recovery. Irrigation collapsed. Agricultural land went fallow. The Tigris became clogged with debris. The urban core that had supported one of the Islamic world's major cities was broken. The Mongols spared some artisans and scholars. Among them was Nasr al-Din al-Tusi, a leading astronomer. He later joined Hulagu's court and helped establish the Maraga Observatory in Persia. However, the majority of Baghdad's libraries, religious schools, and archives were destroyed. The House of Wisdom, already in decline, disappeared from history after the siege. Surviving institutions relocated to Cairo and Damascus. Baghdad never again held the same intellectual or political weight. The impact extended beyond Iraq. Trade routes through the Tigris Valley were disrupted. Caravans diverted westward. Tax records from subsequent decades show a sharp decline in revenue from Mesopotamian provinces. In the decades following the conquest, population levels in central Iraq dropped. With irrigation systems in ruin, farmland reverted to marsh or desert. Attempts by the Ilkhanate administration to rebuild the region yielded only partial success. The broader regional consequences connect Baghdad's collapse to climate anomalies. Volcanic eruptions like the 1257 Samalis event released large quantities of sulfur dioxide, forming aerosols in the stratosphere that reduce global temperatures. These changes last for 1 to 2 years. The 1258 eruption, based on ice core data and climate modeling, was one of the most powerful in recorded history. Its effects were felt in Europe, Asia, and the Middle East. The cooling disrupted harvests, created famine, and strained political systems already facing internal tensions. Though no sources from Baghdad mention the eruption, that absence is not unusual. Medieval chroniclers did not have the tools to recognize distant geological causes for local climate change. They documented famines, strange weather, and floods, but rarely linked them to volcanic events thousands of kilometers away. The silence is consistent with how climate shocks appear in historical texts, fragmented, localized, and often unexplained. In Baghdad's case, the military assault is the event most often remembered, but behind it were conditions that magnified the damage. Poor harvests weakened the population. Infrastructure was already under stress. Environmental disruption reduced the city's capacity to resist. The Mongols, though decisive in their campaign, encountered a city primed for collapse. The fall of Baghdad was swift, but the groundwork for its failure may have been laid by an eruption whose ash never touched its soil. The smoke that reached the moon. In the year 1258, records from distant parts of the world describe strange atmospheric conditions. In England, the chronicler Matthew Paris noted that the sun appeared weak and dim, unable to warm the earth. In France, Salambene de Adam wrote of cold weather and failed harvests. In Japan, the Azuma Kagami reported late frosts and irregular crops. These scattered observations pointed to a shared cause, yet no visible source was identified. No volcano was mentioned. No mountain was seen erupting. Still, something had darkened the skies, and its effects were global. Modern analysis now links these reports to a massive volcanic eruption that occurred in late 1257 or early 1258. The eruption was large enough to send sulfur dioxide high into the stratosphere, where it formed a dense layer of aerosols. These particles blocked sunlight, cooling the planet. Ice core samples from Greenland and Antarctica both show a sharp sulfate spike in 1258. It remains one of the largest in the last 2,000 years, indicating a volcanic eruption of extraordinary force. Unlike eruptions that deposit ash locally, stratospheric aerosols from tropical volcanoes can travel globally. They circulate through atmospheric currents and reflect incoming solar radiation. As a result, temperatures drop worldwide. Tree ring records from Europe and Asia show reduced growth beginning in 1258. In England, agricultural records reveal crop failures and food shortages. In Norway, tax documents from the late 1250s reflect reduced yields. These are indirect signs of a climate event with no obvious source. Lunar eclipses in 1258 and 1259 were recorded as darker than usual. Though the observers could not explain the cause, today it is understood that atmospheric dust from volcanic eruptions can make lunar eclipses appear unusually dim or red. The term smoke that reached the moon is used in modern descriptions to explain how high the aerosols rose, far above normal cloud layers, well into the stratosphere, and high enough to alter the color and brightness of the moon during an eclipse. At the time, no one could connect the climatic symptoms to an eruption. There were no satellite images or global monitoring systems. The eruption had occurred in a remote region with little written documentation. For centuries, its location remained unknown. It was only in the 21st century that scientists identified the likely source, Mount Semelas, part of the Rinjani volcanic complex on Lombok Island, Indonesia. In 2013, a team led by Frank Levine conducted geological surveys of the region. They found thick deposits of volcanic material and a massive caldera consistent with a catastrophic eruption. Radiocarbon dating of buried vegetation placed the event around 1257, directly aligning with the ice core data. The eruption was estimated to be at least a VEI 7, making it one of the largest in recorded history. The eruption sent enormous quantities of ash and sheet into the upper atmosphere. The sulfur dioxide formed aerosols that remained suspended for over a year. These particles scattered sunlight, lowered surface temperatures, and disrupted weather patterns. Monsoon cycles shifted. Harvest seasons were altered. In China, historical records note unusual weather and crop failure. In the Andes, sediment cores suggest increased rainfall and flooding. These effects were indirect but widespread. In Europe, food shortages followed the cooling. In 1258, England saw grain prices double. Parish records show increased death rates in some regions. In France, monasteries noted hunger and poor growing conditions. Religious leaders held special masses to address what they believed were divine warnings. In Scandinavia, chroniclers mentioned difficult winters and reduced harvests. Though the language was theological, the underlying cause was environmental. In the Middle East, chroniclers such as Ibn al-Farad mentioned hardship in 1258, but attributed it to war and unrest, particularly the Mongol sack of Baghdad. However, the broader region also saw reduced agricultural productivity. Trade routes were disrupted, and cities dependent on food imports experienced shortages. Egypt, which relied on the Nile's annual flooding, also recorded anomalies in flood levels during this time, suggesting climate disruption extended across North Africa. The impact of the eruption continued into 1259. Atmospheric models show that global cooling persisted for at least 2 years. The growing season in many regions was shortened by several weeks. In mountainous areas, glaciers advanced slightly. These changes, though subtle, placed pressure on societies already managing political or economic instability. The mystery of the missing eruption remained unsolved for centuries. Without a written record of the event itself, historians and scientists had to rely on physical clues, ice layers, tree rings, and volcanic deposits. The identification of Mount Somalis closed a major gap in the understanding of 13th century climate history. Though no medieval source mentioned it by name, its eruption shaped the environment across continents. The term smoke that reached the moon captures the scale of the eruption's effects. Though no one saw the eruption directly, the consequences were visible in the sky, on the land, and in the documents left behind. Lunar eclipses grew dark. Crops failed. Populations suffered. The event had global consequences, yet its cause remained invisible to those it affected. In hindsight, the 1257 eruption offers an example of how natural forces can shape human history without leaving an obvious mark in the written record. The eruption was unseen, the ash fell silently, and the sun dimmed for months. Yet across the globe, it left a trail of eruption that can still be measured today, in ice, in trees, and in the pages of forgotten chronicles. The famine Europe forgot. In the year 1258, Europe faced a food crisis. Crop failures across England, France, the Low Countries, and parts of Italy were widespread. Yet, unlike later famines, this one left few detailed records. Chroniclers wrote little. Royal proclamations were rare. But administrative data, monastic records, manorial accounts, and market logs show unmistakable signs of scarcity, hunger, and economic strain beginning that year. In England, the Chronicle of Bury St. Edmunds noted that wheat prices had risen sharply. A bushel that sold for 4 pence the year before now cost over 10. At Westminster Abbey, records show that meat and grain allocations to monks were reduced in the summer of 1258. The manorial rolls of Essex and Suffolk reveal lower yields, fewer livestock, and missed payments from tenant farmers. In the Yorkshire accounts, rents were deferred or converted to labor. The economic pattern suggests an abrupt disruption of the agricultural cycle. These effects were not confined to England. In France, abbeys in Normandy and Anjou recorded poor harvests. The Cistercian monks of Clairvaux postponed construction projects in 1258 due to lack of surplus grain to feed laborers. In Paris, market regulations were issued to prevent hoarding. Across Flanders and Brabant, landowners petitioned local courts to delay tax collection from peasants who had lost their crops to frost and rain. Ice core data from Greenland confirms that 1258 coincided with one of the largest sulfate deposition events in 2,000 years. The sulfate spike is consistent with a tropical volcanic eruption, likely Mount Somalis in Indonesia. The stratospheric aerosols from this eruption caused global cooling. In Europe, this meant shorter growing seasons, unseasonal rainfall, and a series of harvest failures. Tree ring data from Germany and Poland shows reduced growth in 1258 and 1259, indicating colder than average temperatures during key agricultural months. Spring rains in 1258 were heavier than normal. In southern England, sowing was delayed. In northern France, waterlogged fields prevented harvesting. In the Low Countries, drainage systems were overwhelmed. Barley, oats, and wheat failed to ripen in time. In cities, the effects were immediate. London's bakers reduced loaf sizes. Parisian records indicate grain prices more than doubled. Laborers could no longer afford daily bread. Petty theft increased, as seen in court rolls. In rural areas, the situation worsened. Parish records from East Anglia show a spike in burial entries. Clergy noted deaths from weakness and hunger. though plague was not mentioned. In Florence, almshouses admitted more children than usual, many orphaned or abandoned. In Flanders, wool production declined as sheep feed became scarce. Weavers and dyers in Ghent and Bruges slowed output due to raw material shortages. International trade offered little relief. Baltic ports, including Lübeck and Danzig, received fewer grain shipments. The Hanseatic League's records from 1258 show disrupted trade routes and delayed deliveries. In Pisa and Genoa, maritime logs report smaller cargoes. Local merchants in London and Rouen raised prices sharply on imported grain. But with most of Northern Europe affected, no region had true surplus. Despite the widespread impact, the famine of 1258 is not well remembered. The Great Famine of 1315 to 1317 overshadowed it in historical memory due to more dramatic narratives and longer duration. But the earlier famine was likely more sudden. It struck without warning and coincided with political distractions. In England, barons forced King Henry III to accept the provisions of Oxford in June 1258. Chroniclers focused on political reform, not environmental hardship. Evidence of the famine's reach comes from unexpected sources. The University of Oxford saw a drop in enrollment in 1258 and 1259. Fewer students could afford housing and food. In Bologna, university accounts show reduced tuition revenues. These changes align with broader economic contraction during the famine years. Education, like food, depended on surplus. Aristocratic households were not immune. Letters from the estate of the Earl of Gloucester mention concerns about grain shortages. In one case, a request was sent to York for extra provisions to feed household staff. Noble families had stores, but even these ran low. Some sold off livestock early to afford grain imports. The scale of disruption crossed class lines, even if the poorest suffered most severely. Some monasteries tried to respond. The Abbey of Saint-Denis opened its granaries to surrounding villages. In Winchester, the bishop authorized emergency food distributions from cathedral stores. But these efforts were limited in scope. Monastic reserves were not designed to feed entire regions. Once exhausted, they could not be replenished. Urban authorities attempted regulation. In London, the city council issued edicts against grain hoarding. In Paris, bakers were forbidden from raising prices without permission. But enforcement was inconsistent. In Cologne, grain riots broke out in early 1259. Officials were forced to import emergency supplies from the Rhine region, but the shipments were insufficient. By 1260, the famine began to ease. Harvests improved slightly but remained below average. Many tenant farmers had defaulted, some never returning. In Kent and Essex, land was abandoned, reassigned, or left fallow. Rural uncertainty pushed people into towns. Lords consolidated holdings, and some villages never recovered. Though the famine lacked lasting cultural memory, its economic effects are clear in records. The 1258 famine showed how deeply medieval life depended on climate. A single eruption from Samalas, unknown to Europe, caused widespread hunger. No English chronicler knew its source, and no French monk understood the darkened skies. Yet the result was shared: shortened growing seasons, failed crops, and quiet starvation spreading through homes, towns, and monasteries, leaving behind scars in both land and ledger. The ash that changed empires. In early 1258, the city of Baghdad was one of the largest and most influential centers in the Islamic world. It housed the House of Wisdom, where scholars translated Greek, Persian, and Indian texts. Trade routes ran through its streets, connecting it to Damascus, Cairo, Samarkand, and the ports of the Persian Gulf. But in February of that year, the Mongol army under Hulagu Khan breached the city's defenses. Over the course of a week, tens of thousands were killed. The Abbasid Caliphate collapsed. The Mongol conquest is well documented. What is less studied is the environmental backdrop: a volcanic eruption in 1257 whose atmospheric effects reached into the political and military shifts of the mid-13th century. The eruption of Mount Samalas injected an enormous quantity of sulfur dioxide into the stratosphere. This reduced global temperatures for several years. Tree ring data, glacier records, and written accounts all reflect a multi-year period of climate disruption beginning in 1258. Crops failed, growing seasons shortened, water supplies diminished. Though the environmental consequences were indirect, they coincided with major upheavals. The Mongols, under the leadership of Hulagu, were executing a plan devised by Möngke Khan to subjugate the Muslim world. The campaign began in 1256 with the destruction of the Nizari Ismaili strongholds, including Alamut. Baghdad fell in 1258. Later that year, Mongol forces attempted to advance into Mamluk-controlled Syria. But in September 1260, at the Battle of Ain Jalut, they were defeated by the Mamluks. It was the first major Mongol defeat in the West and a turning point in the expansion of their empire. While the reasons for the Mongol defeat at Ain Jalut were tactical and logistical, the broader environmental conditions likely played a role. Rivers across the region were running lower than average. The Orontes and Euphrates had both experienced diminished seasonal flow. Rainfall in Syria during 1258 and 1259 was unusually sparse. Livestock died in greater numbers. Mongol supply lines, already stretched, encountered difficulty in provisioning their cavalry. The Mamluks, drawn primarily from slave soldiers trained in Egypt, had greater access to stable resources due to the Nile's reservoir systems, though even the Nile had shown signs of abnormal flooding patterns during this time. In China, the Yuan dynasty had not yet been established, but the Mongol state in the north was already engaged in managing food distribution challenges. The climate disturbances affected crop yields in the Yellow River Basin. In 1259, Möngke Khan died during the siege of Diaoyuqing, halting the Mongol advance in southern China. Though his death was caused by illness, the prolonged campaign was complicated by extended supply chains and weather disruptions. Some sources note that the region suffered from rain and shortages. Again, these were indirect effects, but they occurred in proximity to key military events. In Europe, where the Holy Roman Empire was in a period of political fragmentation, no decisive collapse occurred, yet individual regions reported grain shortages and peasant unrest. In Hungary, the court of Belfort had only recently recovered from the Mongol invasion of 1241. The volcanic cooling of 1258 put added pressure on its fragile economy. The Balkans saw increased taxation to manage food scarcity. While no large-scale wars erupted, administrative documents from Bohemia and Transylvania note drops in tax revenue and delays in agricultural collection. The Byzantine Empire, already weakened by internal strife and the Latin occupation of Constantinople, experienced poor harvests in 1258 and 1259. Records from Mount Athos monasteries mention a reduction in stored grain and fewer visiting pilgrims. The Empire of Nicaea, one of the successor states, struggled to maintain trade flows across the Aegean. Maritime routes were disrupted by inconsistent winds and supply shortages. These disruptions undermined the logistical backbone of minor powers already stretched by territorial ambition. The Kingdom of Sicily, under the rule of Manfred, was caught in a broader conflict with the papacy. The environmental crisis of 1258 intensified internal dissent. Sicily experienced famine and inflation. Manfred's reliance on Muslim soldiers and unpopular taxation deepened his unpopularity. Though his final defeat came in 1266 at the Battle of Benevento, the preceding years were marked by internal economic strain that weakened his position long before the battlefield. The African continent also felt the aftershocks. In Ethiopia, the Zagwe dynasty was navigating internal succession disputes. Regional rainfall data reconstructed from lake sediment cores suggests reduced precipitation in the late 1250s. The Horn of Africa experienced cooler, drier conditions. Though few written records survive from the region, oral traditions describe periods of low harvests and pastoral migration during this time. In India, the Delhi Sultanate under Nasiruddin Mahmud saw slowed architectural and cultural output during these years. Though the state was not directly threatened, inscriptions and building records show fewer projects initiated between 1258 and 1260. Grain prices in North India reportedly increased. Climatic shifts may have constrained agricultural production, limiting revenue. Across continents, these patterns repeat. Political tensions escalated in regions already weakened by environmental stress. In some cases, as in Baghdad, the timing of collapse intersected directly with the global atmospheric changes. In others, climate disruption eroded resilience over time. Mount Simolas erupted in a remote part of the world, but its effects penetrated imperial borders, taxation systems, and military campaigns. The ash that circled the globe altered more than the weather. It influenced decisions, delayed conquests, and destabilized empires that, under ordinary circumstances, might have endured longer or expanded further. The mystery in the ice. In the early 1980s, researchers analyzing ice cores from Greenland encountered an unexpected anomaly. Within the layers dated to the mid-13th century, specifically around 1258, there was a sharp spike in sulfur concentration, far greater than anything recorded in the preceding several centuries. The scale of the deposit was on par with, or even exceeded, that of the eruption of Tambora in 1815, which caused the year without a summer. Yet in the case of the 1258 spike, no known volcano had been recorded erupting at that time. There were no surviving chronicles in Europe, the Middle East, or East Asia describing a major eruption. It was, as scientists later described, a signal without a source. The ice cores, sourced from sites such as GSP-2 in central Greenland, provided year-by-year climate data. Each layer, formed by annual snowfall, trapped particles from the atmosphere. By measuring the levels of sulfuric acid and ash embedded in the ice, scientists could infer the scale of volcanic eruptions and their geographic spread. The layer corresponding to 1258 contained unusually high sulfate levels and tiny glass particles consistent with volcanic material. A corresponding signal was also found in cores taken from Antarctica, indicating a massive tropical eruption whose plume had reached both hemispheres. The absence of a contemporary written record for this eruption puzzled researchers. Large eruptions typically leave visible effects, unusual sunsets, failed crops, or tsunamis. But apart from the climate anomalies and famine conditions reported in 1258 and 1259, no direct observation of an eruption had survived in historical texts. Some scientists propose that the eruption must have occurred in a remote or uninhabited area. Others speculated that it may have taken place in a region where records were later destroyed or suppressed. For decades, the location remained uncertain. Candidates were proposed and eliminated. Mount Etna in Sicily and Iceland's Katla were initially considered, but geological dating did not match. In the early 2000s, new studies using volcanic glass signatures pointed researchers toward Indonesia. On the island of Lombok, near Mount Rinjani, lies a massive caldera known as Sagara Anak. Beneath it are the remains of a volcano known as Mount Samalas. Geological evidence suggested that Samalas had erupted in the 13th century and had subsequently collapsed, forming the present-day lake. In 2013, a team led by French volcanologist Frank Levine published findings confirming that Mount Samalas was the likely source of the 1257 to 1258 eruption. Radiocarbon dating of charred tree remains, along with geochemical analysis of tephra layers, placed the eruption precisely in that window. The scale was catastrophic. Volcanic material had buried nearby settlements under meters of ash. The eruption column likely reached 40 kilometers into the atmosphere, dispersing aerosols globally. It would have taken only weeks for these particles to reach the poles, where they were trapped in the ice. The impact of the eruption, though invisible in contemporary writings, became increasingly clear in physical records. Tree ring datasets from Europe, Asia, and North America all showed reduced growth in 1258 and 1259. This confirmed that the eruption had led to lower global temperatures. The estimated temperature drop was between 0.7 to 1.3 degrees Celsius on average, enough to shorten growing seasons and disrupt rainfall patterns across continents. The archaeological record in Lombok also supports a major event. Excavations revealed abandoned irrigation channels, damaged temples, and thick ash deposits extending over a wide radius. No written records from the Samalas eruption have survived from local sources, possibly due to the destruction of nearby communities. The court chronicles of the Majapahit, or earlier Javanese kingdoms, do not contain mention of the eruption, which may suggest that the affected population did not have written traditions or that the records were lost during later conquests or colonial erasures. Even with the identification of Samalas, certain questions remain. The lack of a tsunami record in the Indian Ocean is unusual given the eruption's scale. No significant earthquake damage is documented either, which is rare for such a massive geological event. Some climatologists suggest that the eruption may have occurred in stages, with multiple venting episodes instead of a single explosive moment. This could explain the extended period of climate disruption without corresponding catastrophic short-term damage to coastal cities. Further complicating matters is the near silence of Chinese, Arab, and South Asian sources. In Chinese astronomical records, which were typically detailed in observing unusual celestial events, there is no mention of an ash cloud or a dim sun. This may suggest that prevailing wind patterns push the volcanic plume westward and northward, away from East Asia. Alternatively, the effects may have been gradual enough to avoid drawing attention in official annals. Satellite imagery, combined with LiDAR surveys of Lombok, shows the topography of the caldera in greater detail. The estimated volume of ejected material exceeds 40 cubic kilometers, making the Samalas eruption one of the largest of the last 2,000 years. Its absence from historical memory underscores how even global events can be lost when they occur outside the administrative and literary centers of their time. In the present, this mystery in the ice serves as a reminder of the limits of written history. Without the ice cores, the eruption would remain unknown. Without cross-disciplinary analysis involving geology, climatology, and archaeology, the global implications would remain misunderstood. The ice trapped more than just sulfur and ash. It preserved evidence of a catastrophe that reshaped human lives far beyond the region where it occurred, even if no one at the time knew exactly where it began. The monks who spoke in code. In the summer of 1258, a Benedictine scribe at the Abbey of St. Albans recorded a note in Latin that described a strange dimming of the sun and a year in which the heavens seemed to labor. The account was not detailed and made no mention of an eruption or natural cause, but when compared to similar notations from other monasteries across Europe, it becomes clear that something unusual was being recorded, often in vague, symbolic, or coded terms. The monks did not speak openly of famine or catastrophe. Instead, they wrote of signs, omens, and spiritual disturbance. The result is a puzzle, widespread acknowledgement of abnormal conditions, but cloaked in the language of theology, not meteorology. The Chronicle of Matthew Paris, also of St. Albans, provides one of the most widely cited accounts. He noted that the sun gave no warmth and described an epidemic of murrain among livestock, followed by great scarcity of grain. He attributed these signs to divine displeasure. No natural explanation was offered. In this, he reflected a worldview common in the mid-13th century. Climatic phenomena were interpreted through a religious lens. Events such as eclipses, floods, and droughts were often seen as moral judgments or tests of faith. This framework appears in texts from multiple regions. In the monastery of Tyniec, near Krakow, scribes wrote of a darkened season in 1258 where processions were held to pray for the return of sunlight. The Annals of Marbach from Alsace described a cloud that lingered over the fields and poor harvests without cause. In Spain, the Cistercian monks of Poblet wrote of suffering and silence that fell over the countryside. The vagueness is consistent. While these monastic records note hardship, they avoid technical or naturalistic language. They do not use terms like ash, eruption, or cooling. At the core of this interpretive pattern was a lack of scientific models to explain climate anomalies. Aristotelian natural philosophy, still dominant in scholastic circles, did not include knowledge of volcanic aerosols or stratospheric dynamics. Atmospheric changes were believed to result from imbalances in the four elements or divine will. As a result, monks recorded phenomena that today are recognized as environmental disruptions, but did so using allegory and religious motifs. Some historians have suggested that this language functioned as a kind of code, less in the sense of secrecy and more in the sense of interpretive framing. The scribes did not intend to obscure reality, but described it in the only terms they had available. For instance, references to fire in the heavens could refer to red sunsets caused by ash particles. Mentions of the sun losing its strength may describe reduced solar radiation due to volcanic haze, but these descriptions remain ambiguous unless cross-referenced with physical evidence. The consistency of these symbolic records is striking. In southern Germany, the monks of Reichenau recorded a year of spiritual testing marked by poor wheat and rye. In Ireland, the Annals of Ulster contain a brief reference to a bad year for bread without elaboration. These observations, scattered across thousands of kilometers, suggest a shared experience of hardship, even if the cause remained unnamed. In addition to textual sources, liturgical records from the years 1258 to 1260 show an uptick in special masses and processions. These included prayers for rain, for light, and for deliverance from suffering. In France, bishops in Limoges and Tours issued directives for local clergy to lead communal fasts and vigils. While these practices were not uncommon in the medieval period, their clustering around 1258 points to an unusually widespread perception of crisis. Even as they chronicled the physical effects of famine and crop failure, monks preserved their interpretation within theological frameworks. Hunger was a test of virtue. Diminished light was a call to repentance. These interpretations shaped the historical record, obscuring natural causes that are now identifiable through ice cores, tree rings, and geochemical data. Not all monastic records were abstract. In northern Italy, the monks of Monte Cassino described reduced snowfall in the winter of 1258 and poor yields of olives and grapes. These observations are rare in their concreteness. In Norway, the clerical community in Bergen noted that fishing yields dropped for 2 consecutive seasons. Such entries, though more empirical, remain limited in number and geographic scope. Language played a crucial role in shaping how these events were remembered. Latin, the lingua franca of educated clergy, offered a limited vocabulary for natural phenomena. Words like caligo, darkness, fragus, cold baying, and fames, famine, were used broadly and lacked precise meteorological distinctions. Descriptions often borrowed from biblical imagery, plagues, exiles, darkness over the land, further reinforcing a spiritual framing. It is in this context that the coded nature of monastic records becomes clear. These were not scientific logs, but theological diaries. The monks wrote not to explain nature, but to interpret it. Their priority was not documenting physical causes, but drawing moral lessons. In doing so, they left behind a mosaic of testimonies that require careful decoding when viewed through the lens of modern climatology. This challenge is compounded by loss. Many monastic libraries were destroyed in subsequent centuries, during wars, reforms, or fires. Some of the most valuable records that may have included detailed accounts are gone. What remains is partial, fragmented, and mediated by centuries of transmission. Yet even in this fragmentary state, the echoes of the 1258 disruption persist in the prayers, the fasting calendars, and the guarded notes in margins about a sun that failed to warm and crops that failed to grow. When the Nile failed to flood. In Egypt, the lifeblood of the land was the Nile. Its annual inundation, typically occurring between June and September, was not just a geographic event, but an organizing principle of agriculture, taxation, and time itself. The success or failure of the flood determined the region's food security. In most years, the river would rise steadily, fed by rains from the Ethiopian highlands. But in 1258, in the years immediately following, the flood levels fell short. Records from Cairo and Fustat, though sparse, describe an unusually low Nile. The consequences were immediate: diminished harvests, economic pressure, and strain on the Mamluk regime that had only recently come to power. The Mamluk Sultanate had emerged in 1250 after the overthrow of the Ayyubid dynasty. By 1258, Sultan Qutuz held power, and the new regime was consolidating its authority amid external threats from Crusaders and Mongols. The Nile's failure to flood properly in those years added another layer of instability. Tax revenue from agricultural output decreased. Grain became scarcer in urban markets. Bread prices rose. These effects were noted in Arabic sources, though not always with explicit attribution to the Nile. The 13th century chronicler al-Makrizi, writing in the early 1400s, preserved earlier reports of food shortages and price inflation, especially in periods following weak floods. He noted that in years where the Nile failed to reach the ideal level of 16 cubits at the Nilometer in Cairo, officials grew concerned. Though al-Makrizi does not mention 1258 by name, the pattern he described matches climatic reconstructions showing regional drought. Modern analysis of sediment cores from the Nile Delta supports this. The composition of certain layers, particularly those laid down in the late 1250s, indicates a reduced water flow consistent with below-average Nile flooding. The nilometer, an ancient measuring structure built on the southern tip of Rhode Island, was still in operation at the time. It recorded the river's height in cubits, with 16 considered the baseline for a good flood. Measurements below 12 cubits usually triggered official responses, price controls, rationing, or prayers. While the primary records from the nilometer's measurements in 1258 have not survived, indirect evidence from administrative records suggests a substandard flood that year. Elsewhere in the Islamic world, scholars and theologians interpreted environmental disruptions through both religious and political lenses. The lack of a strong flood was viewed by some as a divine test. Religious leaders called for fasting and public prayer. These responses are reflected in Friday sermons recorded in Cairo and in manuscripts preserved in the Dar al-Kutub. The theological framing of the event mirrors the approach taken in European monastic communities, though the context and language differed. At the same time, the Nile's failure occurred amid broader climatic changes that had begun with the 1257 Samalas eruption. Atmospheric aerosols released by the volcano reduced solar radiation, affecting the monsoon systems that fed the Ethiopian highlands. With diminished rainfall in the region of Lake Tana, the primary source of the Blue Nile, the volume of water reaching Egypt dropped. Satellite-based reconstructions of East African precipitation confirm anomalously low rainfall during 1258 to 1260. The link between the eruption and the Nile's behavior was not understood at the time, but it is clear today through interdisciplinary study. The economic repercussions of a weak flood extended beyond food. Many Egyptian craftsmen relied on predictable agricultural cycles for their income. When grain yields fell, purchasing power declined across the economy. Urban tradesmen, dependent on the surplus produced by rural farmers, saw fewer orders. Textiles, pottery, and other goods experienced a drop in demand. This is noted in the declining number of new waqf, charitable endowment, documents from 1258 to 1260. Wealthy patrons delayed or canceled projects, which was an indirect signal of financial strain. The Mamluk government, still young and facing geopolitical threats, had to manage the dual burden of external war and internal scarcity. In 1260, the year of the Battle of Anjalut, the state was already under pressure. While the military victory over the Mongols is well documented, the preceding logistical challenges remain less explored. Climate disruptions likely influenced provisioning and morale. Troop movements required food, water, and animal fodder, all of which were in shorter supply than usual. The Nile's low flood also affected transportation. Boats relied on high water levels to navigate inland canals and trade routes. With reduced flow, some channels became impassable. Merchants reported delays, and grain shipments between Upper and Lower Egypt were disrupted. This further contributed to price inflation in urban centers like Cairo and Alexandria. Letters preserved in Geniza documents, written by Jewish merchants, mention delayed deliveries and unexpected shortages during these years, though again, no specific cause was named. The agricultural cycle of Egypt was thrown off balance. Farmers planted fewer crops. In some regions, fields were left fallow. Livestock perished due to limited water and feed. The long-term consequences included soil degradation in areas that were not properly irrigated. In the context of a multi-year disruption, the cumulative effect was a contraction of agricultural productivity. Some villages along the Nile Delta recorded population declines, inferred from abandoned dwellings and a drop in tax records. While Egypt did not collapse during this period, it experienced measurable stress. The environmental trigger, the suppressed monsoon, originated far beyond its borders, in volcanic ash spread across the stratosphere. Yet the impact was intensely local. The failure of the Nile to flood was not just a natural anomaly. It was a systemic shock that reached into markets, religion, governance, and survival. The plague that came before the plague. In the historical imagination, the Black Death of the 14th century dominates as the defining epidemic of medieval Europe. But in the year 1259, nearly a century before the more famous pandemic, there were reports of widespread disease that affected large portions of the population. The timing closely followed the failed harvests and climatic disruption that began in 1258. Though not described in the same language or with the same clarity as the later plague, evidence from across Europe and parts of Asia indicates a mortality event, likely tied to weakened immune systems, poor nutrition, and secondary infections made worse by environmental collapse. In England, the chronicler Thomas Wykes, writing at Osney Abbey near Oxford, described 1258 and 1259 as years of great mortality. He linked it to famine, noting that many died not only of hunger, but of a foul illness that followed. Wykes did not name the disease, but his testimony joins several other reports that record high death tolls in the years immediately following the atmospheric dimming and crop failures of 1258. In the Annals of Dunstable, another monk noted that the graveyards were full. The pattern extended across the British Isles, with Ireland's Annals of Connaught reporting a sickness upon the land. Further south in France, similar phrases appear. The Annals of Saint-Denis refer to 1259 as the year of pestilence, though details are few. In Germany, the Limburg Chronicle described many deaths in the towns, and in parts of Italy, bishops were recorded as conducting special rites for the dead. While these entries lack the dramatic language used during the 14th century plague years, they suggest that communities were reacting to a sustained and unusual mortality pattern. The diseases likely included dysentery, respiratory infections, and possibly typhus, illnesses that spread rapidly among weakened and malnourished populations. Modern epidemiological studies have tried to reconstruct this earlier plague using burial records and climatological data. At the Cambridge University Department of Archaeology, isotope analysis of skeletal remains from rural cemeteries in eastern England found signs of nutritional stress concentrated around the late 1250s. There was an increase in mass graves, and signs of childhood stunting rose in samples dated to this period. Though the cause of death cannot always be confirmed, the pattern points to a spike in mortality that was not due to warfare or local violence. In the Low Countries, city records from Bruges and Ghent show a decline in guild activity and property transfers in 1259 and 1260, consistent with population loss. Some cities temporarily suspended market days, and tax records show a dip in revenues. Although these do not explicitly confirm a plague, the indirect indicators, reduced economic activity, increased orphanage admissions, and adjustments to burial practices, suggest a health crisis of considerable scale. In the Byzantine Empire, the historian George Pachymeres recorded disruptions in Anatolia that may relate to similar outbreaks. He mentioned both climate abnormalities and sickness among the peasantry, though his focus was primarily on military affairs. Arabic sources from the Mamluk Sultanate likewise note famine-related deaths, but only occasionally refer to disease explicitly. This silence does not necessarily mean the absence of illness, but reflects the nature of record-keeping and religious framing of catastrophe. In East Asia, there are fewer references to disease in 1259, but it was a critical year for other reasons. The Mongol Empire under Mongke Khan launched a campaign into China that was abruptly halted when Mongke died during the siege of Diaoyucheng. Contemporary sources in China suggest that disease was circulating among Mongol troops. The history of UN records the emperor's death without specifying cause, but later commentators noted the possibility of illness spreading in the ranks. While this cannot be directly tied to the European outbreaks, it aligns with the global impact window triggered by the 1257 eruption and the ensuing disruptions. The mechanism linking the environmental event to epidemic disease is indirect but understood today. Widespread crop failure, reduced sunlight, and colder temperatures led to food shortages. Malnutrition weakens immune responses, especially in children and the elderly. Poor sanitation in densely populated towns, combined with stagnant water and colder weather, fosters outbreaks of gastrointestinal and respiratory illnesses. The result is a cascading health crisis, even in the absence of a singular pathogen like Yersinia pestis. There is also evidence that communities sought spiritual explanations. In Catalonia, monastic texts describe 1259 as a year of divine anger. In some areas, flagellant processions were recorded earlier than their usual 14th century appearance. Special days of repentance were declared in parts of Hungary and Bohemia. The alignment of famine, sky darkening, and disease contributed to a climate of fear and religious anxiety, laying the cultural groundwork for how later plagues would be interpreted. Although it is difficult to quantify the full scope of mortality, the event that followed 1258 was not isolated. It was a multi-regional experience. Archaeobotanical data from Switzerland shows a decline in cereal pollen around 1259, which suggests either reduced planting or population loss. In Scandinavia, historical sources are scarcer, but burial sites in parts of Denmark show higher than average interments. The evidence is cumulative, pointing to an episode of disease that accompanied the environmental strain of the period. In medieval texts, plague often meant any deadly illness. Without microbiological evidence, historians study burial rates, clergy deaths, orphans, and legal records. After 1258, these signs suggest a health crisis, less known than the Black Death, but one that revealed the vulnerabilities later exposed by the pandemic of 1347. The Ashfall Conspiracy. In the decades following 1258, very few sources directly referenced any singular catastrophic event that could explain the widespread environmental and social disruptions recorded across multiple continents. Instead, references to dim skies, failed harvests, and disease appeared scattered, fragmented, and contextually isolated. What is absent from nearly all accounts, however, is the mention of volcanic ash. Despite the evidence that points to one of the most powerful eruptions of the last millennium having occurred just 1 year prior. This silence has led some researchers to question whether the lack of direct commentary was an accident of record-keeping or the result of intentional omission, either due to interpretive frameworks of the time or later editorial choices by institutions and chroniclers. The eruption in question is now identified through scientific means rather than historical texts. Ice core samples from Greenland and Antarctica show a massive spike in sulfur deposition around 1257 to 1258. These sulfate markers are comparable to, and in some layers exceed, those recorded for the 1815 Tambora eruption. Yet where Tambora produced a global record of descriptions, colored sunsets, sudden cold, volcanic fogs, the 1258 event left little descriptive evidence in writing that can be definitively linked to ashfall. The disconnect between scientific data and textual records is unusual. One explanation is that ashfall did occur, but the people witnessing it lacked the language or framework to understand what they were seeing. Descriptions of dust, dark clouds, or heavenly veils appear in records from France, Syria, and parts of Germany, but they are vague and often couched in theological terms. The 13th century mindset lacked a geological vocabulary. There was no conception of the atmosphere being altered by volcanic material from thousands of miles away. What they saw might have been interpreted as celestial or moral disturbances rather than natural phenomena. Yet in areas likely to have experienced ashfall directly, particularly around the equator or southern Asia, the written record is even more sparse. The Majapahit and Singasari kingdoms in Java, both active in the 13th century, left no clear record of an eruption. The Javanese Nagara Kretagama, compiled later in the 14th century, does not mention a 1257 eruption, though it discusses other events in broad terms. Chinese sources from the Yuan dynasty era also omit any direct reference to ashfall, even as they note strange weather and failed crops. The absence is notable. One hypothesis is that ash did not fall heavily in populated areas, but remained aloft in the stratosphere, influencing climate without visible deposits. This is supported by modern climate models, which show that the sulfur aerosols from a high-magnitude eruption can encircle the globe and suppress temperatures without depositing thick ash layers in distant regions. Still, the complete lack of regional narratives describing black rain, falling cinders, or respiratory problems caused by airborne particulates remains an anomaly when compared to the records from more recent eruptions. Another line of inquiry considers the possibility of post-event censorship or redaction. Some historians argue that church or court chroniclers may have intentionally avoided attributing social or economic collapse to a physical cause. Instead, they framed disruptions as divine punishment or moral decline. This would have reinforced the authority of religious or royal institutions, which benefited from interpreting crisis as an opportunity for repentance or reform. Theologians and monks often copied manuscripts decades later. A lack of understanding or ideological motivation may have led to selective emphasis or omission of volcanic descriptions. The lack of coordination among contemporary chroniclers adds to the mystery. In 1259, England, France, the Middle East, and parts of Asia all recorded food shortages and bad weather, but few, if any, connected these phenomena to a global or regional source. Today, this pattern is sometimes referred to as distributed amnesia, a situation where multiple groups remember symptoms but not the cause. This idea was advanced by historian Robert Siegel, who proposed that medieval societies recorded trauma in pieces, leaving later researchers to reconstruct the full picture using natural science as the connecting tool. In recent decades, volcanologists and paleoclimatologists have worked together to fill the gap left by the historical record. Satellite models of aerosol movement, tree ring data from Scandinavia and Central Asia, and glacial chemistry all point to a singular massive eruption. The consensus now points to the Samalas volcano in Lombok, Indonesia, as the most likely source. But the identification did not occur until the early 21st century, when researchers including Frank Levine conducted fieldwork near Lake Sagara-Anak and uncovered pyroclastic deposits that dated precisely to the 1257 timeframe. Despite this, the historical narrative has yet to catch up. Textbooks and popular history often overlook the 1258 event entirely. Museums do not exhibit artifacts labeled as post-Samalas ashfall recovery. Medieval history courses rarely mention a mid-13th century environmental catastrophe of this scale. The result is that the ashfall silence has persisted, not only in the medieval period, but into the modern academic framework. Whether this silence was accidental or institutional remains debated. Some scholars argue that the patchy communication networks of the time made large-scale comparisons of climate records impossible. Others suggest that rulers and chroniclers benefited from ambiguity, using vague language to control the political narrative during a time of hardship. Without a written vocabulary for geological disaster, and without the political will to explain collapse as anything other than divine or moral failing, the ash simply disappeared from collective memory. Today, evidence confirms a major 1257 eruption with global climate effects and widespread crises in food, health, and rule. Yet it remains strangely absent from medieval records, an event felt by millions, but remembered by almost no one. The hidden source, Indonesia or Iceland? The eruption that triggered the global disruptions of 1258 has no medieval name. For centuries, no chronicler recorded its location, no traveler described its crater, and no analyst linked it to the worldwide crop failures and climate anomalies that followed. It wasn't until the late 20th century that scientists began to connect sulfate deposits in polar ice cores with a massive volcanic event. But the origin of the eruption remained uncertain. Two primary candidates emerged: Indonesia, particularly the Samalas volcano on Lombok Island, and Iceland, known for frequent and powerful eruptions that have historically disrupted weather across Europe. The first clues pointing to a massive eruption came from ice cores drilled in Greenland and Antarctica. In 1980, glaciologists working with the Greenland Ice Sheet Project reported a distinct spike in sulfate concentration dating to around 1258, with matching layers in the Antarctic core. This indicated a high-altitude stratospheric injection of sulfur dioxide on a global scale. The volume of material when compared to known eruptions like Krakatoa, 1883, and Tambora, 1815, suggested an even larger event. But because no eruption had been recorded in 1258 by European or Asian chroniclers, the source remained unidentified. For decades, Iceland was considered a probable origin. The island had produced catastrophic eruptions in historical times, including the Laki eruption of 1783, which caused widespread famine and atmospheric haze throughout Europe. Medieval annals in Iceland were carefully maintained at monasteries such as Þingeyrar and Hólar. However, researchers found no record of a major eruption in or near 1258. Icelandic sources did mention regional hardships, but nothing approaching the magnitude that would explain a stratospheric aerosol veil blanketing the globe. Moreover, Icelandic tephra, volcanic ash with distinctive chemical signatures, was absent from geological samples linked to the 1258 sulfate layer. Attention shifted to Southeast Asia. In 2012, a team led by French volcanologist Frank Levine began investigating the caldera of Rinjani volcano on Lombok Island in Indonesia. Rinjani contains a large crater lake, Sagara-Anak, and within it a volcanic cone known as Barujari. But historical records suggested that another volcano, now collapsed, had once stood adjacent to it. Levine's team identified a massive deposit of pyroclastic flows and pumice layers, radiocarbon dated to the mid-13th century. These deposits were far larger than those from recent eruptions, indicating a caldera-forming event. Radiocarbon dating of charred tree trunks buried beneath the volcanic material produced calibrated dates between 1257 and 1259. The stratigraphy matched the timing of the ice core sulfate spike precisely. Geochemical analysis of the volcanic glass matched the signatures found in polar ice, linking the eruption at Lombok to the global climate disruption. The volcano was identified as Samalas, a mountain that no longer exists in its original form, but once stood alongside Rinjani. It had collapsed during the eruption, forming the Sagara and Nak caldera. Historical support for the event was later found in a Javanese manuscript, the Babad Lombok. Though written in the 17th century, it preserved an account of a great eruption that destroyed villages and forced survivors to flee. While the chronology is approximate, the narrative described a powerful mountain explosion, clouds of ash, and entire settlements buried, a rare native textual echo of the eruption. Despite this, debate persisted. Some researchers questioned whether a tropical eruption could fully account for the Northern Hemisphere effects. They proposed a two-eruption model, one in the tropics and another in the Northern Hemisphere. But further examination of sulfate dispersal patterns indicated that a single equatorial eruption could, under the right conditions, affect global climate. Stratospheric wind patterns would have distributed the aerosols poleward, leading to the matching sulfur layers in Greenland and Antarctica. Climate simulations using the Community Earth System model supported this theory, showing how an eruption of Samalas's magnitude would have cooled the Earth by over 100 degrees for several years. Additional confirmation came from dendrochronology, tree ring data from the Northern Hemisphere, particularly in Europe, Siberia, and North America, showed suppressed growth starting in 1258. This pattern matched those observed after the Tambora eruption in 1815 and Krakatoa in 1883. The abrupt tree stress, combined with documentary sources describing failed harvests, made it increasingly clear that the Samalas eruption was the singular cause. By 2013, the Bulletin of Volcanology published Levine's findings, identifying Samalas as the most likely candidate. The eruption was classified as a VEI-7, Volcanic Explosivity Index, placing it among the largest known in the Holocene. Its estimated ejecta volume exceeded 40 cubic kilometers. The eruption cloud likely rose over 43 kilometers into the atmosphere, injecting sulfur dioxide directly into the stratosphere, where it formed sulfate aerosols that reflected sunlight and cooled the planet for years. Today, Indonesia remains one of the most volcanically active regions in the world. Yet the memory of Samalas vanished from cultural memory, erased by the collapse of local societies and the absence of consistent written records. Unlike Krakatoa or Tambora, which erupted in the age of global communication and Western observation, Samalas erupted in relative obscurity. Its impact, however, was no less global. Iceland, while initially considered, ultimately lacked the physical and historical evidence to support the theory. No eruption of sufficient size was found to match the timing or geochemistry. The mystery that had lasted for more than 7 centuries was finally resolved not through medieval chronicles, but through volcanic ash, ice layers, radiocarbon dating, and climate modeling. A convergence of disciplines that now forms the basis of paleoclimatology. The source was hidden, not by conspiracy, but by distance, illiteracy, and the passage of time. Samalas was not forgotten because it was insignificant, but because it erupted in a world unprepared to record its full meaning. Lost cities, forgotten causes. The disappearance of entire communities in the mid-13th century has long been noted by archaeologists and historians, but often interpreted in isolation. Each settlement attributed to war, disease, migration, or local economic collapse. Yet a closer examination of the timeline reveals an unusual clustering of abandonment and decline around the years 1258 to 1262. These events correspond directly with the environmental shock caused by the eruption of Samalas in 1257 and the subsequent global cooling, crop failure, and famine. When viewed collectively, they raise the question, how many of these vanished settlements were lost not to local circumstances, but to a planetary event that left no name in contemporary memory? In the British Isles, researchers have identified several medieval villages that were deserted in the decades following the mid-13th century. While the more famous wave of abandonment associated with the Black Death occurred in the 14th century, earlier disappearances have been found in East Anglia, Northumberland, and parts of Yorkshire. The village of Warham Percy, later excavated and often tied to post-Black Death decline, began showing signs of depopulation in the late 1250s, long before the pandemic of 1348. Manorial records reflect declining rents, and pollen analysis from soil cores around the site shows a sudden drop in cultivated grains around 1260. In Germany, the region of Thuringia shows similar anomalies. Settlements mapped through LiDAR and archaeological digs reveal buildings left unfinished and plow layers that abruptly stop being used. The disappearance of these communities cannot be fully explained by war or political upheaval. In many cases, there is no sign of violence or forced migration. The abandonment seems instead to follow a pattern consistent with food scarcity and environmental hardship. In Bohemia, parts of the Elbe River Valley experienced similar reductions in population, with ecclesiastical records showing a decline in baptisms and marriages beginning in 1259. The pattern extends to the eastern Mediterranean. In parts of Anatolia, once thriving trade routes show sudden interruption in tax ledgers and market documentation. Caravanserais, inns built to support traveling merchants, saw a reduction in usage in the early 1260s. The Armenian Kingdom of Cilicia, which had been actively engaged in trade with Europe and the Mongol Empire, experienced a series of unexplained interruptions in revenue collection. While political tensions and military campaigns undoubtedly played a role, they do not fully account for the simultaneous decline across multiple regions. In the Middle East, particularly in the Levant, archaeological sites show a decline in urban maintenance. Drainage systems in cities like Aleppo and Damascus were left unrepaired, contributing to the spread of disease. Grain storage facilities were found with the spoilage layers indicating inadequate turnover, signs of food not being replenished as expected. At the time, chroniclers attributed many problems to divine displeasure or moral decay. But there is growing evidence that environmental collapse, rooted in the 1257 eruption, was a contributing cause. Further east, in the Khmer Empire, the city of Angkor began to experience a shift. Although the final decline of Angkor occurred in the 15th century, new remote sensing studies have revealed that its water management system, one of the most sophisticated in the pre-modern world, suffered stress starting in the late 1250s. Droughts, alternating with intense monsoons, put pressure on reservoirs and canals. Sediment analysis from the Westbury Reservoir shows disruption during this exact period. The environmental anomalies traced to the Somalis eruption may have impacted rainfall cycles across Southeast Asia, destabilizing a civilization built on hydraulic infrastructure. In Central America, the timing is less precise, but radiocarbon dates from Maya sites like La Joyanca suggest a second wave of abandonment events around the 13th century, long after the classic Maya collapse. Though not directly tied to the 1257 eruption, this clustering of environmental stress suggests that global atmospheric events had ripple effects far beyond their epicenter. Even small temperature shifts could alter rainfall patterns in regions dependent on seasonal water sources. In Japan, temple archives and agricultural logs note that rice yields dropped sharply in 1258 and 1259. Some villages in the mountainous regions of Honshu and Kyushu show a halt in expansion during this time. In several cases, shrine donations and religious festivals were suspended, a pattern often linked to economic distress. The records do not explicitly mention climate, but tax collection dropped significantly. Combined with evidence from tree ring data showing suppressed growth, it adds to the picture of a prolonged environmental downturn. What links these otherwise unconnected cities and regions is their simultaneous strain. None of them were aware of a volcano erupting in Indonesia. None had a global view of climate, yet all experienced outcomes consistent with a short-term but severe environmental shock. Diminished harvests, rising mortality, loss of trade, and migration. In isolation, each settlement's decline could be attributed to local misfortune. Together, the patterns suggest a coordinated response to an unrecognized global event. Modern techniques like radiocarbon dating, palynology, and geochemical soil analysis now allow researchers to reassess old conclusions. Sites once believed to have been abandoned due to economic failure are now being revisited with an eye toward environmental indicators. In some cases, the findings suggest that these communities were unable to adapt to abrupt climate shifts, leading to famine, disease, or migration. These conclusions are supported by increased evidence of skeletal stress markers in excavated graves, signs of malnutrition and chronic illness that began suddenly around 1258. The loss of these cities left no epic tales, no battles, no flames. Their absence in history reflects not insignificance, but a slow disaster. Cold summers, failed crops, and fading order. The volcano's name and the cities vanish from memory and together. The Vatican's weather silence. The archives of the Vatican contain some of the most detailed records of medieval Europe, maintained continuously by scribes, secretaries, and church officials over centuries. During the 13th century, the papal states were not just religious authorities. They were administrative centers, recording everything from land grants and legal disputes to celestial observations and famine relief efforts. Yet for the period spanning 1257 to 1261, amid one of the most severe global climate disruptions in recorded history, there is a noticeable scarcity of commentary on weather-related catastrophes in papal documents. This omission is particularly striking when compared to the well-documented reaction of the Church during the later Great Famine of 1315 to 1317. The papacy of Alexander IV, who reigned from 1254 until his death in 1261, coincided directly with the aftermath of the Samalus eruption. His tenure covered the crucial years in which food shortages and unusual weather patterns would have been affecting much of Europe. Yet papal correspondence from this period, preserved in the Registra Vaticanae and other archival series, contains little in the way of specific references to failed harvests, solar dimming, or mass starvation, phenomena that were extensively reported in regional chronicles outside Rome. This discrepancy has drawn attention from modern historians attempting to reconcile the silence with the physical evidence of crisis. There are a few scattered references in ecclesiastical letters to poor harvests and high food prices, but they are framed as local inconveniences rather than symptoms of a broader catastrophe. In letters from French and English bishops to the papal court, some complaints about rising grain costs appear in the early 1260s, but they are not treated as urgent or systemic. Instead, the focus remains on political and doctrinal matters, heretical movements, bishopric appointments, and relations with the Holy Roman Empire. The contrast with later famines, which prompted direct papal appeals for prayer, fasting, and almsgiving, is difficult to ignore. One theory for this silence is bureaucratic inertia. The papal curia may have been slow to recognize the scale of the disaster due to its distance from agricultural regions most affected. The court was often mobile during this period, moving between Anagni and Viterbo, and may not have experienced the same intensity of hardship as urban centers in northern France or England. However, the administrative machinery of the church extended well into those territories, and regular correspondence with regional dioceses suggests that the papacy was not entirely unaware of the disruptions. Another possibility is that the papal silence was intentional. The mid-13th century was a period of increasing emphasis on church authority, and admitting to an inexplicable environmental disaster may have been seen as a challenge to the theological framework of divine order. Without a clear doctrinal interpretation, some church leaders may have chosen not to highlight what they could not explain. The concept of a volcano affecting global climate was entirely foreign to medieval thought. Natural disasters were interpreted through a moral lens, as punishment for sin or evidence of divine will. But the 1258 disruptions lacked an obvious moral narrative. They affected both the pious and the wicked, disrupted sacred and secular life alike, and offered no clear target for repentance. This theological uncertainty may have led to avoidance. Theologians such as Thomas Aquinas, writing during this very decade, were working to reconcile Aristotelian natural philosophy with Christian doctrine. Aquinas' work focused heavily on logic, causation, and divine order. Yet he made no mention of the 1258 famine or unusual weather, despite its relevance to discussions on divine justice. His silence may reflect the broader discomfort of the intellectual elite with phenomena that did not fit existing explanatory models. Furthermore, the Vatican archives of this period underwent periods of reorganization and selective copying. Many original documents from the 13th century survive only in later transcriptions, made by scribes in the 14th or 15th century. These copies were not always complete or neutral. Political documents were prioritized, while mundane records, including those related to local events or weather, were often discarded or overlooked. As a result, it is possible that more detailed accounts of the crisis once existed, but were lost through administrative filtering. Nevertheless, peripheral church records do offer indirect glimpses of the impact. Monastic registers from Benedictine and Cistercian houses across Europe show disruptions in tithes and land productivity between 1258 and 1261. These monasteries, many of which operated farms or collected agricultural rents, recorded unusually low yields and in some cases the inability of tenants to meet obligations. Yet even these accounts rarely connect their difficulties to environmental causes. The language remains abstract, speaking of scarcity, misfortune, or divine trial, without identifying the specific chain of events that led to such outcomes. Liturgical changes, which often marked periods of crisis, were not widely implemented during these years. Unlike in later famines, when special masses were held to invoke rain or divine mercy, the Vatican's liturgical calendar in the late 1250s remained largely unchanged. This suggests either a lack of recognition of the scale of suffering or a conscious choice to treat the disruptions as routine rather than exceptional. The result is a peculiar historical vacuum. While local chronicles, scientific data, and archaeological evidence all point to the 1258 event as a turning point, the Vatican's central records present it as an uneventful period. The reasons for this gap remain debated, whether they lie in limited awareness, selective documentation, or theological discomfort with unexplained catastrophe. What remains is a portrait of institutional continuity. The Church focused on doctrine and diplomacy during a major natural crisis. Its silence on the disaster is now studied itself, revealing as much about medieval structures as any preserved document or written account. The Vatican's silence in 1258 wasn't just an absence, it was a message, a mystery still buried in forgotten pages. If you found this story compelling, subscribe for more hidden histories and untold truths. Like, share, and stay curious. Because sometimes what's missing is the most revealing part of the story,